All right, let's go.
Hello, everyone, and welcome to our presentation, a method of securely comparing integer using binary trees. This is a joint work with Jonas this is a colleague, former colleague who is now at University of Bochum, and David, who is still working at SAP. So the motivation of our work is, let's say we have a server with a computation, with a function, and on this side we have a client who want to evaluate his input on the server's data. So we assume that the client data is sensitive and maybe also the output of the computation, and the function as well can be sensitive. This is why they can use secure computation to do that kind of computation. In this talk, we will focus on integer comparison, where the input of the client is a single value, and the value of the input of the server is another value y, or a function or a function representing y. So this kind of integer comparison has been used in different applications like machine learning, benchmarking, enterprise benchmarking, where companies can compare their KPI securely, but also in biometric authentication. Regarding related work, there are different protocols using, for example, the binary representation of the input, or they can represent the input as integer, also floating point. And the schemes that are used to do this kind of computation are Gabel circuit, or additive homomorphic encryption, or fully homomorphic encryption. In our work, we focus on binary representations using homomorphic encryption. So this means that we assume that we have a public and private key that is generated by the client, and the public key is revealed to the server. We can do computations we can do addition, homomorphic addition on ciphertext, and also multiplication. If the schemes support only addition, then it is additive homomorphic, but then you can still have operations like adding constant, or inverting a ciphertext, or multiplying by a constant. Also, a very interesting operation is computing exclusive OR, where we have an encrypted bit and a plaintext bit, and we can compute the exclusive OR homomorphically. All those operations are also possible with fully homomorphic encryption, but we can also do those operations when both inputs are encrypted. So the intuition of our work is, I will illustrate it with this example, where x for the client is 2 and y is 3. So we start by, on the server side, we represent a tree for all strings of length 3, because the inputs here have bit length 3, and we label the leaves from tree with 1, because we want to check whether x is larger than 3. This 3 can. It is easy to see that we can prune this tree, because everything that goes from here we land to a leaf labeled with 1, and we can even go a step further by focusing only on leaves that represent a 1. Now, to do the computation, we will let the input of the client encrypted bitwise and send it to the server. So I will use the blue color for FHE and the green color for AHE. So what we do is, having the input of the client, we just traverse the tree with the encrypted input of the client. So if it is FHE, we actually compute equality bits between the input and the edge labels. So this means that here, for example, we compare these bits and this one, and because they're equal, we have a 1 here. and we have a 0 here. For AHE, we use inequality. This means that we will have 0 and 1. After that, we just aggregate the bits on the path. So this means for FHE, we do here multiplication. We'll have here a 0, a 0, a 0, and 0. For AHE, we do it using an addition. This means that we'll have here a 1 and here a 1. For the remaining leaves, we will just choose random ciphertext. If the input were, for example, 4, then we will have the situation where we have exactly one. We have exactly 1 here, 1 time, and then we can add all those homomorphically to have an encrypted 1. For AHE, we will have exactly a 0, and the remaining ciphertext will be random ciphertext. So because we cannot multiply with AHE, we will send those inputs permitted in a random order to the client, and the client will decrypt it. If he finds a null, a 0, then this means that the input is larger. There are situations where we can assume that the input of the client, both inputs are actually encrypted. So this means that Y is also encrypted. And the server can no longer use the tree like this because he doesn't know how to generate the tree. It is easy to show that to see that by permitting the node in the tree. You can have a tree with this in this form where we can where the leftmost path is labeled with the bits of Y, and then we have to because here we have a 0, we must have here the negation, which is a 1. We have here a 1. We must have here a 0, and also this leaves is labeled with 1. And the remaining leaves are labeled exactly with the same value, with the same values of these edges. Now we can do this. We can use this to compute on to evaluate the client input as before. We can do the computation also using an array instead of a tree. This turns out to improve the performance a little bit. So this means in this case we will so the first column here represents the leftmost path, and the second column represents these edges here, and these are the leaves. So, and then we can do the same computation here using the array. So this means that later we'll multiply this value with this one. We will multiply this value so along the rows. The computation can be we can do the computation with AHE as well, but as I said before, we need to reverse the label. So here we had a 0. Here we had a 1 for FHE. We have a 0 here, and the other leaves will be reversed as well. The other leaves will be reversed as well, and you can also we then have to evaluate the client input on this tree. Before we use inequality test by doing an XOR. Now with FHE, with AHE, we have the problem that we cannot do XOR anymore because XOR needs 1 bit unencrypted. So it is easy to, so we then notice that we can do this by using subtraction, by just subtracting the bits. And then after evaluating the client inputs, we have something like this. Then we have another problem. If the input of the server of the client was 6, for example, we have a situation where we have 2 zeros on 2 paths, while we need to have exactly 1 0. To solve that, we just multiply with increasing powers of 2's, and this results in the leftmost path encoding -3 and no longer 0. So we also contributed another optimization for FHE, which allows to reduce the depth of the multiplication, because if you are using level FHE, the depth of the multiplication is relevant. And instead of multiplying like this, we can first multiply these bits and this one, and later multiply this one, and then we have a depth of 2 instead of a depth of 3. We can pre-compute this computation and use it later in the online computation. So to summarize, the result, we implemented the schemes and some related work, and using AHE, we can improve when the 2 bits are when only one of the bits are encrypted, and also even when both bits are encrypted, we have even more better performance. For FHE, the performance is a little bit worse compared to related work, but the memory consumption was about 10% better. So to summarize, we contributed integer comparison using binary trees. The schemes is non-interactive, meaning that we actually do a single interaction with the server. Our schemes can be implemented using AHE and FHE. We theoretically analyze our schemes, implement them, and evaluate them. Thank you.
Let's get the other speakers set up while we take questions for this excellent talk. Any questions from the audience, please, again, use the Zulip. Let me check. Okay, I think we do have a question. So a question from Dimitris Mouris. Are you comparing the whole trees, or are you just comparing some paths as you showed on slide 7? If you are comparing the whole trees, isn't this inefficient? If you are not comparing every path, doesn't this leak information?
We need to compare the whole tree because we need to avoid revealing which part of the tree.
So performance is maintained as you compare the whole tree. Cool. Thank you again for this excellent presentation, and let's get set up with the next speaker.